And my point of interest is maximal inequalities and regularity of the stochastic convolution process. And first, I want to define the setting. In my first work, I was working in a Hilbert space of a Fian-Seidler. That means I take a Hilbert space, and A can be unbounded and A is a linear unbounded operator generating a C0 group of contractions. And what is this? I call it usually by T. And what is the point of interest? The point of interest is this process, that means this stochastic convolution process. And what are the difficulties? The difficulties is more or less that this is not a martingale. That means that you cannot apply directly the martingale in inequalities. And this exists only for positive. And inequalities of this type of maximal regularity in time was shown by several authors, several peoples.
Do you have some process psi in front of W?
Yes, psi of S and psi yes. There you can Prato.
So it's WH value or it's
It has a finite Hilbert-Schmidt norm. This is the set of
yeah, psi has finite Hilbert-Schmidt norm, but the W is cylindrical.
Yes, it's cylindrical. Yes. Lunardi. If you look at the literature, there are a lot of people look which as a topic the maximal inequalities, and what I proved with Jan Seidler was the following. C. And the idea of the proof was quite simple. I want only to write down in fact, this is we took a dilation theorem from G, which tells us the following. Take if A of t r if I have a C0 semigroup of contractions, and that means ETA smaller or equal than 1, then there exists a Hilbert space H, a unitary group U T an adwedding from isometric such that the following is there exists a Hilbert space H, a uniform group U of T, and an isometric embedding I, such that this diagram commutes. And this is quite easy to apply. Using this dilation theorem, this maximal inequality is really straightforward. In fact, the main idea is, if you write the first few lines, to put in here the the unitary semigroup, that means E, T minus S, and the embedding. Then you can put this outside, and you have and if you look at this here, this is a deterministic process, and this here is really progressive, and the T is not inside. So here you can apply the Burkholder maximal inequality, and this here you can give an estimate. So taking expectation on both sides. So here you apply the Burkholder-Davison inequality, the usual one. Then you get this here you can give here an estimate, and then you get the result. The next question we had in mind is how to generalize it, for example, to other martingales. And in fact, this is also quite straightforward. If you have a general martingale, you can generalize this type of inequality to a general martingale. But here I have to introduce first some notation. Where's the
sorry, I'm not sure. Why did you have to introduce I and so forth? Doesn't Burkholder's inequality just apply to that if you, because it's a contraction? Because the original semigroup is a contraction?
If it's a contraction, the T is here and here, so this is some you can't if you take the supremum, here over the T is here and here, so you have you can write it at 1 and as a characteristic function until time t, but then you get it only for a fixed t, but you want to have a t in an interval.
Okay, and so the other way, so what does, okay.
Here you can't apply the Burkholder directly.
I think the point is that the u is invertible, so you can pull it out of the integral.
If you lifted the contractional semigroup to a unitary semigroup, that it's invertible, you can put the u in front.
All right, well, good.
But here directly it doesn't work.
So the process is a product of a time-dependent function times a stochastic integral. And this, for the about the stochastic integral, we know that it has continuous trajectories. But to represent it as a product, I think Erika needed this theorem.
Relation theorem.
But the fact that the semigroup is contraction is essential,
This is essential.
even for the relation theorem.
Yeah, I found even a more general dilation theorem for finite cotype, Banach spaces of finite cotype, but I guess there's also that the semigroup has to be of contractions. So this is essential. This is two more general processes. And here we take again a Hilbert space H. And good. Bubble. And here we look at H, where H is a Hilbert space, and we look at the set of square integrable H-valued Catlett martingales.
Sorry, just one more question. Can you give an example of this theorem with the I and the theorem that had the commutative diagram? I mean, what would be an example?
For example, from the semigroup of the Laplacian, then this can you lift up to a unitary.
Can you say what it is?
What
If
it
you take,
is.
if I may interrupt, if you take a shift semigroup on the half line, positive half line, then it is a contraction,
Yes.
but it is not unitary.
Right.
So now, if you take now L square on the whole line and take the shift semigroup.
Okay, so you keep the part that was lost.
Yes, so this is the extension.
Okay. Very
Yeah,
good.
so it is unitary, and it is an extension.
Okay, good.
But I must say, it is maybe a good question. If you take a contraction semigroup on the real line, so simply e to minus at, where a is positive, so it is on one-dimensional space, then the extension is still infinite dimensional. No, because e to minus at is not unitary. But the theorem is saying that there exists a unitary. So it is really, I think it's a nice exercise, how to define this extension in the simplest case.
But what you're losing is really the smoothing property and these things. So these things you're really losing. So you can't use anymore if you take the Laplacian, the smoothing. So
one nice class of examples where you can very easily construct this extension explicitly is like in the case of the heat equation. If your semigroup is a Markov semigroup, which in the case of the heat space, then you can actually take your big Hilbert space, kind of space of stochastic processes, and the projection operator would just be the expectation, the unitary semigroup, the unitary group, just be the shift operator in the space of stochastic processes. So in the case of the heat semigroup, your big Hilbert space or Banach space or so would just be space of stochastic processes which would just be run in motion. And then your projection operator is just the expectation. And the unitary group is just the shift group.
So the extension is from deterministic functions to processes? Or?
Yeah, but
So-
then
so-
that's again a Banach space. Space of all stochastic processes.
That's nice. Yes. For martingale or semi-martingale, one can introduce a bracket, and this bracket is n is the I see Broca's predictable process, the process, adapted process. And the bracket is this process such that this is a martingale. And now the same inequality looks like the following.
So you are considering n square, you are in Hilbert space, so do you have a real valued bracket or a tensor bracket there? I don't know. So n square?
It should be the norm, I
It's the
think.
norm, so it's
Yeah.
So
it's not a tensor.
it's the,
It's a real value.
Yeah.
Erika, I didn't understand. Are you talking about the Meyer process or the quadratic variation? So
The quadratic variation. So the Meyer is the predictable. So in this case, you have the Burkholder-Davis inequality, which is simplified. So I think everybody knows it. And applying this kind of Burkholder-Davis inequality, you get the same here. If you have here dn of s and CE of 0t C of s. I'm used to Poisson random measures, so I never know how to write it nicely in this setting. And you get this inequality if you apply it. And maybe what is also interesting for if you come from Brownian motion, this is a random process. So this is not deterministic. So often this gives you difficulties.
But I have some problems.
Yeah.
No, I mean, if you have, because you are in a job case, so maybe it's related to the question of Islam. But first of all, the Burkholder-Davis works for Q bigger than some value, I think, bigger than 1. So it doesn't work for all the cases. And the quadratic variation, so you have the oblique bracket and this one. Are you sure that the one that you get here is the one that makes this process a martingale? Because it's more related to the sum of discretization or something.
And quadratic variation.
It's a quadratic variation.
That's wrong. It is a in both cases. In both.
And I think it holds for all Q.
In the jump case, there are some counterexamples. The jump case, yes, there are some counterexamples which come back to monad and so on.
You can't, I have here not the Meyer bracket. So if you have the Meyer bracket, you have Q has to be smaller than 2 or equal to. But if you have here the bracket, which is random process, it holds for all
I agree.
Q.
This one, no, not for all Q bigger than 0. Now there are some counterexample of the paper of Monat about the validity, but in any case, for Q bigger
Larger
than
than
1, that's sure. But
I think Davis is for Q equal 1.
Yes.
So now,
in the
so
jump case,
we will,
yes, in the jump case, there are some differences. That's for sure.
say for semi-martingales, you are saying, because I think
For local martingale.
So this counterexample is about local martingale or about martingale?
I'm speaking about the jump case.
Yeah, but you mentioned the
I
word
don't
local
remember
martingale.
exactly. I will tell you, because there is a paper of Monat.
So I think maybe we can
Yes.
move to this later.
Mm-hmm.
Surely they're exact.
Inside your right-hand side, it's square.
Yes. It's a square. Okay. And now the last the thing is this is now a recent work which we're interested Jahui and Bresniak is, can one extend this kind of thing to M-type P Banach spaces, get one some similar inequality in more general spaces? And here I want to introduce the setting we have used there, and in fact we have looked there really on processes which are of which has no Gaussian component. That means Levy processes. And I think everybody. And if we take a stochastic process L, and such a stochastic process is called a Levy process if L starts at 0, L has independent and stationary increments, L is stochastically L has high things, or in this setting, we are using more or less Poisson-Renner measure. And linked from Levy process to Poisson-Renner measure is the following counting measure. That is, if we take a subset B of E, and we define the counting measure
S should be not in A, I guess.
S is. So what we define here, we take A, this is a Borel subset of B of E, and we count all the chunks which belongs to A. Then we can define such a measure which is called counting measure. And what we know from this is really a random variable over, and moreover you can really you can show that n of n is distributed like the Poisson has a Poisson distribution, the parameter of nu of A, and this nu of A is a characteristic from the Levy process. It's related to the characteristic, and also n of t n is independently scattered. That means if you take different A1 and A2 which are disjoint, and if you look at the random variables nt of A1 and nt of A2, then these two are independent. So these are these three properties which the counting measure satisfies, and from this here you can really define a Poisson-Renner measure in a quite general setting. So here you start with a measure of the space. Poisson-Renner measure is set times that means that a Poisson-Renner measure is a measurable function from this probability space into the set of measure of integer valued measure over z times r plus. R plus is the time, and z is where the jumps takes its values, such that this here is 0 almost surely. Eta is sigma additive. And and similarly as before, if I take two sets here, and if I look at this random variable, which is an integer valued random variable, then I know this is Poisson disputed with this parameter, and this parameter is equal to nu of a lambda of I, and nu of a is usually called the intensity of the Poisson random measure, and here is the Lebesgue measure of the time. So these are this is a setting of Poisson random measure, and in this way you can show the same inequality, but we have E is an M-type P Banach space, and maybe shortly what is an M-type P Banach space is these are Banach spaces where certain inequality holds related to martingale differences, such that I can define really the stochastic integral. And A from E to E is a linear operator. C AC is a predictable process, and we have Poisson random measure, which I defined here, and space Z, and the measure nu is again related to this Poisson random measure. And here we get the inequality A of the supremum. And here we get this inequality, and by U tilde I define the Cadillac modification.
Of what? What is U?
U is a stochastic convolution process, but U tilde.
But one moment. Stochastic convolution with respect to the Poisson measure?
With respect is so U of S is 0t t minus S A psi of S set
U of t, probably.
U of t is this process, the stochastic convolution process, and U tilde is a Cadillac modification. That means there exists a Cadillac modification U tilde of the stochastic convolution process U, such that this inequality holds.
And now psi are what?
Psi is a predictable process from here to LPC. Here's the intensity on E.
And Q is larger than P.
Q is larger than P. And what here the problem is, if you want to apply this inequality, this is a random process. But one can get it without this thing. But you have to pay a price. P power n. So you get it in a form where here this random process doesn't appear anymore. You have nu, but the PE appears inside. So there's a C. So, if you take the first for I equal 1 and I equal n, then you get once p power n inside, and the other side you get for I equals n minus 1 should be no, for I equals n it has this form, and for I equals 1 you get this form. And this inequality is also the reason that you can't really apply, for example, the trick with the fractional integration.
What trick is that?
In the book of Tabrato and Subject, the article Tabrato, Subject, and Quapien, where you make fractal integration and put it inside, and this you can only apply. You can't apply here in this if you have a Levy process.
Okay, well, I
Yeah.
don't know it, but anyway.
Okay, you can explain later. So I think I.
So we had a lot of questions, we still have 12 minutes. No.
So what you did at the end was very general thing for stochastic integral with respect to
To
a
Poisson-Renner measure.
Poisson measure, yeah.
Yes.
Usually the expectation of the integral.
Mm-hmm.
You can go with the absolute
This is
value.
a joint work with Brezhnev and Jahoui.
Jahoui Zhu. Zhu. Z-H.
Z-H-E.
H.
H. Z-H-E.
Okay. Yes.
I remember that you assumed in the martingale setting stochastic continuity, or in other words, the continuity of the Dubmayer process. Am I right? Or I misheard something?
You mean stochastic continuity?
If I remember well, I'm not sure I remember well, you assumed stochastic continuity on the martingale, in the martingale setting. Was that so, or I couldn't?
Yes, yes, the Cadillac
Not
property.
only Cadillac, but stochastic continuity.
Calculating probability.
Yeah, yes.
Oh, sorry, not quite. Okay. That's
It can
fine.
be
That's
Cadillac.
fine. I saw that you assume stochastic quasi-continuity. That means that, but not that. Okay, that's fine.
This is a continuity in distribution that you
Okay,
assume
I
that the
understand.
distribution is. Okay.
I misheard.
Yeah, that's Sarah.
Is there any relation between the constant, I'm just thinking about optimality of the constant, and the spectrum of the operator A in this inequality?
I think the constant here. Oh, yeah, and also it's related to the Banach space, to the P or Q or which Q you have. This is, and I think the operator A.
It doesn't depend
No.
on the operator A.
So it depends really on E and Q.
Here we Q near to satisfy some additional assumption. The Q's norm, the Q's norm is of C2 class.
Oh yes. That, Q has to be larger than 2. Yes.
Semigroup is a contraction in this theorem, yes?
Yes.
Is it true that if you take a Banach space isomorphic to a Hilbert space, it is n-type 2?
Yes.
Yes.
Symmetric.
Yes.
In fact, Hilbert spaces are characterized to be of M-type 2 and co-type 2.
Sorry. Yeah. So if this is true, does it mean that on a Hilbert space you can have any semigroup, not necessarily contraction?
You have to shift.
If
You can,
the,
you can change the norm.
if what you have in if it's true what you haven't said but you have in mind, that you are right.
You mean the putting in a power minus lambda t
No.
in the norm?
You can introduce a quick, if you have a C0
New norm is an equivalent norm.
you
On
can-
infinite time interval or finite time
It
interval?
depends, but here you need on interval 0 capital T.
Yes, that's true.
But the equivalent norm, so you think that in the equivalent norm, operators are really contractions?
So the semigroup is a contraction.
Yeah.
And it seems that everything works.
Yeah, that's true.
So what is, could you repeat the reasoning that we take a Hilbert space
Yes.
and then what? We know that it is isomorphic.
Isomorphic to a Banach space on which the semigroup is a strongly continuous semigroup of contraction.
But do we know this or?
Oh, this simple fact. Subprimum of this STX.
But but what you, I think maybe we need to discuss it after. But there must be some geometrical issue related to the norm you introduce.
But if you need only M type 2 and it is M type 2,
That's what I'm saying. May not be so.
so you think it's not M type 2?
No, I'm not. I'm saying that one has to look at it more carefully.
But what are the good examples of type 2?
All LP spaces with P larger equal to 2. And Sobolev.
Sobolev spaces.
And the smooth norm, is that included?
Yeah.
The norm is smooth.
There's
So
no,
it's,
once the indices are larger than 2, that's fine.
That's fine, yeah.
And LP,
Larger equal.
And strictly convex, essentially.
Strictly convex is, I think,
UMG.
it's,
Means
type 2
strictly-
it is convex, but not vice versa.
Strictly convex form, I mean, our
It is not equivalent. You can define M type 2 in terms of norms, some two smoothing properties, but strictly convex is not sufficient.
But uniformly convex.
Nice. Okay, are there more questions? It seems not, so we have a longer break than predicted.